This is a lecture introduction to HLSL and DXIL for beginners, part 3 of this series of presentation. So now that we know a lot about input structs and output structs and their role in the shaders, let us look at another example. Here we have an input struct, and we have an output struct, and we have a shader code. Unlike the previous examples, a struct output is being returned instead of a float 4. Now, this is just a generic shader code. It's not like a vertex shader or a pixel shader. It's just a generic demo shader code for demonstrating some important features of HLSL and DXIL. So here in the actual shader code, we notice that we first create the struct output data object, and we return the data object. And then in the middle, we of course fill in the initial values of all the fields in the output struct. Here, data.pair, we are initializing it with a float 2, 0.2, 0.4, and here this data.single, we are just initializing it with a 1.0. However, here this data.triple, we are initializing it with the input.color.rgb, which comes from this input struct, which is given as the input to this shader right here, which means that the output of the shader depends on the input struct. Now, there is an interesting subtle little difference between these two cases. The first one, as in data.pair and data.single, where the shader is generating output data independent of the input, and the second case, as in the data.triple, in which we are passing data from the input into the output through the shader in the graphics pipeline. Now, let's take a look at the DXIL code generated for the HLSL code. I've colored the corresponding coding constructs of the HLSL code and the DXIL code right here. So the first important observation that we notice is that when a struct output is being returned instead of a float 4, although the struct or its corresponding object is never explicitly defined anywhere in the DXIL code, a store output is called for each field of that struct in order to return the data contained within. When you are just storing a constant such as 1.0 or a vector of constants such as float 2, 0.2, 0.4 into an output, you just do the store outputs. However, when you are also taking in something as the input as well, then you also have to do the load input to get that data from the input struct. So here we see, as an example, we're loading the input.color.rgb from the PS input struct as 3 different scalar variables, %1, %2, %3. That correspond to this code right here. And then we are storing the previously loaded scalar variables into the output data, %1, %2, and %3. Now here we are storing the 0.2 and 0.4 into the output data. And also here store 1.0 into this field right here in the output struct, which corresponds to store output call in the DXIL code. Now, in this example with the data.pair, and in this example with the data.single, the shader is generating its own data independently. So we're just storing it out. We don't need the load input. However, in this example with the data.triple, it has to load the data from the input in order to pass it down to the output. Now, we briefly discussed input and output functions in part 1 of the presentation, but I would like to remember that load input and store output takes the input output element ID, which is the unique ID of a signature element metadata record. The element ID is a number like the offset of a field in a struct in LLVM-IR. It identifies which field in the struct to store the element into. For example, when loading from the input.color.rgb, the element ID is 0. Since it is the first field in the structure, and there's only one field in total in the input structure. When storing the 0.2 and 0.4 into the output data, the element ID is 0 because we are storing these numbers into the float2 pair, the first element of the struct output. When storing the scalar variables into the output data, the element ID is 1 because float3 triple is the second element of the struct output. And when storing the 1.0 into the output data, the element ID is 2 because this float single is the third element of the struct output. Similarly, the column parameter is the relative column index. When generating code that assigns values into a float4 variable or any other vector data type, the column parameter is like an index into an array of that vector. When loading the elements from the input.color.rgb, each individual load input is scalarized, meaning that it loads each individual element separately and it indexes each element in the vector using the column parameter. So the first element at position 0 is stored into %1, second element at position 1 is stored in %2, and the third element at position 2 is stored into %3. These temporary variables. And then you store %1 at index 0, store %2 at index 1, and store %3 at index 2 into the output, which matches the order of the elements in the input.color.rgb that were loaded from the input. And here we can see that 0.2 is stored as the first element at position 1, at position 0, and 0.4 is stored into the second element at index 1. And if you interpret this hexadecimal bit pattern as a float constant, you would indeed see that they are 0.2 and 0.4 respectively. Now here, store 1.0 into the output data at an index of 0, since it corresponds to the float single, which can have only one element in. So in conclusion, DXC compiler does not convert HLSL structs into LLVM-IR structs, instead optimizing the code a bit. These load I32 from I32 pointer at dx.nothing instructions are only generated in the 0th level of optimization. They disappear upon higher levels of optimizations, so we can ignore them because they don't really do anything. This is the same HLSL source code as on the previous slide, but now we will look at the AST representation of this code. Let's take a closer look at what this is. First, we can see that we have these two struct declarations of the input and output structs at the top of the AST. Each of these structs is represented as a CXX record decal, and inside these structs we have a field decal for every single field inside this struct. For example, this inside the struct PS input we have a field decal. It is color of data type float4, also known as vector of float, 4. And then attached to the field decal is a semantic decal, which is the color. Similarly, in the struct output definition, we have a field decal, which is a pair of data type float2 or a vector float, 2, then triple of data type float3 or vector float, 3, and then we have a single float, as you can see here. Now after that we have the function decal PS main, which is the shader itself. And then inside of that we have in green parm var decal, declaration of a parameter variable, input of data type PS input, which is this input struct right here. And then we have a compound statement representing all the code within these curly braces. Then we have a semantic declaration at the end with sv underscore targets, which is this sv underscore target right here. Now inside of these curly braces we first have a decal statement, a declaration statement. It's a variable declaration, data variable data of type struct output. Then we are assigning values to each of the fields within that object, and then we are returning this data. So here in the return statement we have a decal ref expression, data of type output. It is a L value, and in order to return that we have an implicit cast of L value to R value. So the first assignment of these three assignments, and all of these assignments are just binary assignment operators right here. They're all just binary operators. So for the first one, on the left side we have data which is of type output, and then on top of that we have a member expression which is dot pair, which is a L value of type float 2 or a vector of float, 2. And on the right side we have this initialization right here. We have this init list expr initialization list expression of data type vector of float, 2, containing the values 0.2 and 0.4. Now, init list expr describes an initializer list which can be used to initialize objects of different types, including struct, class, union types, arrays, and vectors. For example, here, right here, in this example, but here our initialization list consists of 0.2 and 0.4, which is that vector data type. And then around that, we have a CXX functional cast expression, which represents the float 2 that we have right here. CXX functional cast expression represents an explicit C++ type conversion that uses the functional notation, such as in this example. Apparently, the float2, as you see in the AST, is a functional cast expression in HLSL, not a constructor as one might think. It's not a class data type, so there can be no constructor anyway. In the next binary operator expression, we see that the L value is on the left side of the assignment operator, and the R value is on the right side. So this data of type output, around that we have a member expression, which is an L value. That's the dot triple. It's a float 3, and it's a L value. And on the right side, whatever we are assigning is an R value. Now, if an R value is on the right side, there is an implicit cast expression, L value to R value conversion, as we see here. On the right side, we have input.color.rgb. So input, that's of data type PS input, that's the input struct, it's a L value. On top of that, we have a member expression, dot color. That's also a L value, and it's a vector of data type float, comma 4, as we can see right here. And then we have a HLSL vector element expression dot RGB on top of that. So it's a L value vector component RGB. Now it's a L value, but we want to assign it into data.triple. So in order to do that, we have this vector of float comma 3 implicit cast expression L value to R value conversion. And then in this data.single, we have a binary assignment operator again. On the left side, again, we have a data of type output, and it's is a float, L value dot single. And on the right side, we just have a literal float 1.0. So that's the AST representation of this same shader code that we had. Now let's look at this another example, Swizzle with input-output structs. The purpose of this experiment is to see what DXIL code gets generated upon an example of a swizzle. Then the output color is the fields of the input color in reverse order. So we are having float 4 output equals input.color.wzyx. Now, this is our input.color. The fields of the input.color are stored in order into the variables %1, %2, %3, and %4. So here in the DXIL code, x at index 0 gets assigned into %1. Y at index 1 gets assigned into %2. Z at index 2 gets assigned into %3, and W at index 3 gets assigned into %4. W at index 3 gets assigned into %4. So now these four virtual registers, they hold X, Y, Z, and W. And then upon assignment into the output, the fields are reversed. So here we see that %4 is stored into index 0, %4 is stored into index 0, %3 is stored into index 1, %2 is stored into index 2, and %1 is stored into index 3. So we first have these load inputs, and then we have the store outputs. And the result is that the output, as we see here, gets stored with input.color.wzyx, because it was xyzw right here in these virtual registers, but we switched around the orders of assigning these variables into the output. So the colon parameter, which is the second to last field, acts as an index into the float 4, telling it into what position to store the value. It does not matter if you first reverse the input color and then assign it into the output, or if you first save the input color and then reverse the fields upon assignment into the output. The end result is the same, and that is the exact approach that is taken by the DXIL code when you compile the HLSL code down into the DXIL code. Now let's look at the AST representation of this same shader code that we had here. So we had this same input struct with the same float 4 color, same assignment and everything. So here we have the input struct, then we have the function declaration right here, which is PS main. It returns a float 4, and then it has a parameter variable declaration, which is the input of type PS input, as we see right here. Then we have a compound statement with a declaration statement, which is the declaration of this float 4 output and initialization. Then we have the return statement, and finally we have the at the end we have this semantic declaration sv underscore target, which is this sv underscore target right here. So it has all the same AST elements as the previous example shader code that we looked at. But now here are some very interesting observations. First is that we have this input.color.wzyx. We have the input. On top of it, we have the member expression .color, and on top of that, we have the HLSL vector element expression of data type vector float comma 4 L value vector component WZYX. And so the point is that .WZYX is accessed as a vector of float comma 4, which means that it is a vectorized access instead of being scalarized element by element. Whereas when we looked into the DXIL code, we had scalarized loads and stores. The AST is a complete high-level truthful representation of the original shader code. Therefore, we have a vectorized load represented by this HLSL vector element expression right here. Also, we see that we are implicitly casting the L value to R value whenever we want to return something or use it in an assignment expression. So when we want to assign the result of this expression, we have a implicit cast expression, which is a L value to R value conversion. Similarly, when we return this float for output right here, float for output, we have to implicitly convert it from an L value into a R value of data type float 4 in order to return that value. Now, another interesting observation that I didn't go over in the previous example is that the definition of the struct PS input, or any HLSL struct for that matter, in the AST, it contains two nested CXX record decals in the AST. To be more precise, the actual struct or record, which is the referenced struct PS input definition, contains inside of it both the field decal as well as another CXX record decal representing the implicit struct PS input. I honestly don't know why we have such a representation of a simple HLSL struct in the AST, why we have these nested CXX record decal. To me, it seems that only the field decal is necessary, and we could have gotten rid of this extraneous internal CXX record decal. However, in the C programming language, as we see here, we're declaring a similar struct with just one field inside it. There is only one record decal, not two nested ones. So we just have the struct PS input definition, and then we have the field decal of the color, which is a float. So that's a C code, but for HLSL, for some reason, they just decided to have that kind of approach instead. So the shaders that we have been looking at so far have been just in a sequential mode of execution, just instructions going from top to bottom, and that is usually how one would write shader code, just a sequential method of execution. However, if you would need to, HLSL has a feature allowing us to have conditional statements, such as these if statements. So, for example, if you have a sphere, for example, and you want one half of the sphere to be colored purple and the other half to be colored green. So we would have an if statement comparing the exposition to 0. If the input exposition is greater than 0, we color it purple. And else, if the exposition is less than or equal to 0, which is going to this left side, we color it green. So this achieves a half and half effect. If the exposition is positive, one color is assigned, else another color is assigned. This causes the two halves of the sphere to have different colors. So this is the first live shader code that we will look at right now. We will look at this shader code live in NVIDIA FX Composer, and then after that we will look at the DXIL code that is generated. But first we're gonna do a live demo. So here, this is the exact directory where the HLSL for beginners files are being stored. And here we have this HLSL code examples.tar.gz. So copy that and create a directory wherever you want, and just paste that tarball in, and then open up your terminal and navigate to that directory. Since my directory is in the C drive, I will type in cd/mount/c, and then I will enter the name of my directory. And if I look in, I see the tarball inside. And then to unzip that archive, type tar-x vzf, x for extract, v for verbose, z for unzip to get rid of the gzip, and then f to specify the file. So just specify the file, and it unzips it. And if we see there's a HLSL directory that's created with all the code files inside. So navigate to HLSL/FX Composer/sphere textures, and then type in explorer.exe to open this exact directory in the file explorer. And when we see a whole bunch of files related to this project. So the most important one is the fxcproj file. This is NVIDIA FX Composer file. Obviously, you need to have NVIDIA FX Composer installed in order to run this file, in order to see this shader live. I'm not going to go over in this video how to install NVIDIA FX Composer, but it's free and installation is rather easy. So I will click on this and then open with FX Composer 2, or you could just double click on it, and we see the project being opened in the NVIDIA FX Composer. So let's just wait a little bit while it loads. Yeah. So first find the half and half material, and then just double click on it, and that would pop up the HLSL shader source code file. And .fx is a popular file format which is used by NVIDIA FX Composer. It's one of the file extensions that distinguishes HLSL shader source code files. So now looking at this HLSL shader code file, first we have this worldview projection matrix, which we will talk about shortly, but for now it's not our main focus. Instead, we are more interested in these shader structs. First, we have this struct, which is the input from the application. So it's the data that comes from the application into the vertex shader, and it consists of just the input position. And then we have this struct, which is the output from the vertex shader into the pixel shader, which consists of a float 4 position and also a color. Let's take a look at the pixel shader first. This is it just takes this vertex to pixel struct as input, and it takes the input color and assigns it, and it just passes the input color through the pixel shader. So we know that the pixel shader is not doing anything very important. It just takes the a input color that it receives from the vertex shader and just passes it through. So the main code that determines the color is performed in this vertex shader. So the vertex shader basically gets the apt to a vertex in, and as we know, it just consists of the float 4 position. So we take the in.position.x and compare it. If it's greater than 0.0, we assign one color, else we assign another color to this output struct, and then we just return the output struct, we pass it to the pixel shader. So the first thing you gotta do is click on this material right here and drag it into the sphere object and drop it. That will apply the material on the sphere if it's not applied already. And now we can take a look at this scene and orbit the sphere around. And as we see, if the input.position.x is greater than 0.0, which is on the right side of this coordinate plane, then we are assigned this lime green color. And if it's not greater than 0.0, if it is less than or equal to 0, we are assigning this dark purple violet color, and then return out return the struct, and it just goes into the pixel shader and the color just gets passed through. So now that we have seen this HLSL code in live, let's see what it looks like, what the DXIL code looks like when we compile it in Shader Playground in the 0th level of the optimizations with disabled optimizations. So remember that the input from the application consists of just the position. So in our vertex function, this first line right here, the first thing that we do, this line loads the in.position.x into the %1. And then next line we have a comparison statement. We are comparing this %1 to 0.0. So we are comparing this in.position.x to 0.0. Now this is a floating point comparison, and this OGT means ordered and greater than. It yields true if both operands are not a nan, or not a number floating point value, and op1 is greater than op2. So if %1 or in.position.x is greater than %2 or 0.0. And then we have these two statements right here, which basically takes the resulting Boolean value of that and compares it to false. Is it not equal to false? And then assigns that, and it compares, is that %5 not equal to false? And then it branches on that condition. So for some complicated reason though, DXC makes the condition into overly complicated, redundant, inefficient expression when we have these settings, the optimization level set to 0 and disabled optimizations. So in the C source code, it would be like input.position.x is greater than 0.0, and then we take the result of that comparison and compare, is that not equal to false, and then we take that and say, is that not equal to false? So obviously these two are just redundant. So yeah, so we want to get rid of that. And if we set the optimization level to 1, The if condition is now easier to read. So this first line loads the in.position.x into the %1 because we're gonna compare it. We compare %1, is it ordered and greater than 0.0, which is in.position.x, is it greater than 0.0, %2, storing the result of that floating point comparison, and then we branch on that Boolean value %2. If it's true, we branch to this label %3, where we assign this purple color. And if it's false, we branch to this label %4, which assigns this green color right here. And then at the ends of each of these branches in the labels, we then jump unconditionally to label %5 and return void, because both of these if-else branches expressions are mutually exclusive. So here, if we take a closer look, we see these are the hexadecimal floating point values that are stored, and these are the decimal representations. In this purple branch, we are assigning 0.5, 0.2, 0.9, and 1.0. These first three values correspond to R, G, and B, because in the purple branch, in the HLSL code, we see R, G, and B being applied. What is R? It's 0.5 first, 0.5. And then we have G and B, which are 0.2 and 0.9. So we have G and B, 0.2, 0.9. Now in the green branch, these values are in a different order. So they are G, B, R, 0.2, 0.9, 0.5. So we have G, B, which should be 0.2, 0.9, 0.2, 0.9, and then R, which is 0.5 at the end. And this combination produces this lime green color right here. Now, suppose we wanted to visualize this DXIL code into a control flow graph. This same DXIL code, we want to visualize it into a control flow graph. Well, I showed you how to do that in my LVM presentation part 1. What was the command to take a DXIL source code file and generate a control flow graph from that. And when we do that, we see this structure. Yeah, so here we are loading the in.position.x and we are comparing it to 1. If it's greater than, if it's true, we branch to this label %3, do some stuff like store some outputs and branch to label %5 and we return void. And if it's false, we branch to %4 and to %5 and return void. So this is somewhat easier to read. So this if statement that we see right here is actually similar to an example that I had in my presentation, LVM Intermediate Representation for Beginners Part 2. Notice that there are no virtual registers being declared inside both these branching basic blocks because no branch-dependent computations are performed in them. We are only having a store output in each branch. And whenever we are having only a store in each branch without virtual registers, we can collapse the if statement into a select statement, as I demonstrated in that older presentation, LVM intermediate representation for beginners part 2. It is here. Yeah, so we can collapse this if statement into a select statement. And that is exactly what the DXC compiler does under optimization level 3. There is no conditional branching. There is a conditional move instead, greatly simplifying the code. After loading the in.position.x and performing the comparison, which tells us if the x position is indeed greater than 0.0, we have the select statement. So in %3, we select based on if the condition is true, we select 0.5, else we select 0.2. If the condition is true, we select 0.2, else we select 0.9 for %4. And then for %5, if the condition is true, we select 0.9, else we select 0.5. Now we have %3, %4, %5, these 3 virtual registers, and then we store them into the output. %3 goes into the element at index 0 of the return. %4 is stored into the element at index 1, and %5 gets stored into the element at index 2. And this 1.0 is stored into the element at index 3 unconditionally. Well, because it's 1.0 in both of these 2 cases, because it represents the opacity, and we want it to be a solid color. So if you notice, on the left side, that's the if condition which is true. It's the purple color, which represents RGB, because it's 0.5, 0.2, 0.9, 0.5, 0.2, 0.9, and if the condition is false, then we select these colors on the right, which represents the lime color, which is 0.2, 0.9, 0.5. So we got rid of the branching if statement. Now, the only thing I don't like about this is that we have 3 separate individual scalarized selects. The select instruction in LVM intermediate representation is well capable of working with vector types, which would have been more optimized. Instead of having 3 different selects, we could have just selected one value of a vector type containing 0.5, 0.2, 0.9 if it's true, and else if it's false, we could have selected 0.2, 0.9, 0.5. So we would have one select statement instead of 3 for more optimal vectorized, but no, DXIL DXC compiler chose to have them scalarized, probably because this store output function only works with scalarized outputs. But still notice that there is only one basic block this time. If we print the control flow graph, we indeed see that there is no branching at all, which is cool. Now, going back to the NVIDIA FX Composer, we see that this shader code that we applied, it's not that precise. It has some kind of weird blurred effect on these edges. We have a blurred effect right here on the edge, and we have a little blurred effect on the top here, which is not very desirable. We want it to have a sharp edge, but there's a little blurred effect. So why is that? Well, it's because the model geometry interacts with the color interpolation that we have. Uh, Remember that if we take a look back at our HLSL code that we had, we are basically assigning the color in the vertex shader and then returning it to passing it down to the pixel shader. It means what? It means that the color is assigned per vertex. We are basically placing the data into the color slot of the vertex shader, and recall to my previous lecture that any data that is placed into the color slot of the vertex shader gets run through the interpolation unit, and it interpolates that per vertex data into the per pixel data. So in other words, if we had just two vertex data points and we assigned colors to them, and we return that color, then in the middle it goes through the interpolation unit, and there could be 1,000 pixels in between those two vertices, and because there are only two data points, it has to transform them into 1,000 data points for every single one of those pixels. So it just runs the interpolation over those vertex colors to get the pixel colors. Yeah, so our vertex colors are being interpolated between the pixels, and they're interacting with the geometry to get this blurred effect. Notice that in our model geometry, this sphere is composed of these strips of such size rectangles. So in the vertex here, we are only assigning colors to the vertices, each of the corners of these rectangles, and we see that the region where we have these rectangles and this top part right here are precisely where we are getting these blurred effects. It's because we are assigning the colors to the vertices, and because there are no vertices in between, there are no data points in between these vertices, the interpolation unit kicks in and it interpolates between these two data points. And it so happens that because on the left side the data points are purple, and on the right side they are lime green, so it gets interpolated and we are having this blurred effect right here because it interacts with model geometry right here. Now I can show you what the model geometry looks like. To do that, I will just do a typo, create a syntax error, and compile it. Now, in NVIDIA Effects Composer, whenever we have a syntax error, the texture of the shader disappears, and then we just have the model geometry being shown. If we orbit around that and we zoom in, we can indeed see that this sphere is made up of all these weird rectangular slices. So what happens is we are basically assigning vertex color to here, vertex color to here, a vertex color to here, to all of these corners in between these rectangles. But suppose that we're having pixels in the middle where we don't have any data points in between. We're basically getting interpolated values in between these two vertices, and it looks blurry. It looks all messed up. And if we go to the top part, to the top of the sphere, similarly, we see this round circle where we're having a vertex data point in the middle, and then we have a bunch of vertex data points on the outsides, and in the middle, and like in between these two, there's no vertex data point. So that's why we are having interpolation effect on the top as well. So if I remove that syntax error and compile it, we see the vertex shader gets back into the blurred regions in the middle of these slices and in the middle of this. And these blurred effects only happen when we are transitioning from one color to another, because although we have similar slices and large gaps in these halves, but the colors are the same on both sides of the vertices, so when they get interpolated, you don't even notice the discrepancy. Yeah, so that's basically what happens. Yeah, so even though it might look like we're passing the color from the vertex shader and it goes directly into the pixel shader, but it's not the case. It actually gets interpolated over the colors first. So how can we make interpolation work for us instead of against us? How can we solve this problem? Well, the solution would be to assign the color in the pixel shader instead of the vertex shader. So we assign the color of the pixel based on the interpolated position of the pixel. So we get the position of each pixel by interpolating the position of each vertex. That calculates the midpoints between each vertex, and it grabs the position of the pixel at that particular location. And based on the position of that pixel, we can assign then the color. So HLSL doesn't allow you to interpolate vertex positions. If we recall to my previous lecture, only the color or the texture slot in the vertex shader is interpolated, and not the pixel slot. But there is a little trick that you can do. I will show you. In order to go around that restriction, I basically place the input position into the output color slot. Then it gets interpolated, and it comes in as the input color. Now we remember that this input color is actually the interpolated position of the pixel, and we use it as a position despite the fact that this variable is named the color because it comes from the color slot. It's actually the interpolated position. So HLSL doesn't actually care about what data you put into the color slot. It's just numbers, and it gets interpolated like any numbers do. So as far as you're consistent and you treat this as the interpolated value, you're okay. So the net effect of that would be it assigns the color based on the position of the pixel versus assigning the color based on the position of the vertex and then trying to interpolate between these colors. It allows more fine-tuned control over the colors. So here on the left side, we're assigning colors to the vertices and trying to interpolate these colors. Whereas here on the right, we're interpolating the vertex positions to get the pixel positions, and then assigning the pixel positions based on we're assigning the pixel colors based on the interpolated pixel positions. So let's see in this code in action. This is the version of the half and half that is based in the vertex shader. If I click on this, this brings up the version of the half and half inside the pixel shader. If I click this texture material and then drag it onto the sphere, it applies the material on the sphere, and look at that. We are having a precise, clear edge without any interpolation or blurry effects whatsoever, and it looks very clean. So that is why it's important to know about interpolation and what are all of its various quirks. Now we're going to talk about next topic, FX UI elements tweakables. What are tweakables? They are part of the FX framework, a certain way of organizing your HLSL source code files, which is used by both FX Composer and 3ds Max. Tweakables define user interface elements. They are global variables, able to be accessed anywhere in the program. They are stored in the constant registers of the vertex and pixel shaders, meaning that these values are unmodifiable in the shader code in the program, and their values come from the user interface input, as we will see. So the code for a UI element consists of the following parts. First, we have a data type, which is a float4 in this case. Next, we have a name of a global variable, and it can be anything you want, just as the name of any other variable in the program. After that, we have the semantic declaration for UI elements. Now, these serve as a hint to the application using the shader, such as FX Composer, 3ds Max, or a C++ DirectX graphics app, what the UI element is for. It documents the purpose of the UI element. It is optional but very helpful, almost even necessary, because they also have a functionality attached to the semantic declaration. For example, some applications that are using the shader expect your UI elements to be properly marked with these annotations or semantic declarations. If a semantic declaration is absent on a given UI element, or if it is not the correct one, it does not match the element's purpose, it can lead to bugs or potentially even crashes in the user's application, especially in custom C++ DirectX apps, depending on if edge cases are properly handled. But for other applications such as FX Composer, for example, putting a different semantic declaration might result in some minor visual glitches, as we will see in the example below. So those are the semantic declarations for the UI elements. Next, we have these metadata members in the alligator jaws, as I like to call them, the less than and greater than signs. In between, we put these metadata members. These are a bunch of variables with initial values, and as you can see, each one of them ends with the semicolon. You can't just put any arbitrary variables in here though. The data types and variable names must match a set of variables that the graphics application recognizes. For example, this string UI name tells the graphics application FX Composer that this is the name of the user interface element. So as an example, if we open NVIDIA FX Composer backup, we go down, we select this UI elements material, double click to open the code, and then click and drag it into the sphere. And as we can see, the sphere turned this dark gray color. But anyway, this is declaration of the UI element, of the user interface element, and we see here this is the name of the UI element as it appears in this panel right here. If we change this name somewhat and then save it and then compile it again, we see that the name of this UI element in this panel also changed. Now, if we remove this string name from the application, let's see what that does. If we just remove this metadata elements, so now we are having an empty metadata element list. What will happen? So if we compile that, notice that the name of the parameter displayed in the UI element right here would be the variable name, ambient color. We can change it to, for example, a happy color, and then we change it to where it is used in order to not have a bug. And I will show you that if there is no UI name metadata element present, then it would automatically get the name of the variable as the name of the label. We see compiled here, it says happy color. Now let me just reset everything back to the way it was. And the advantage of this UI name is that you can have a totally different variable name and still display a different string in the UI element. Now, going back to our diagram, this last highlighted part in green is the initialization value. This will be the initial value of the global variable in the HLSL code if the user does not supply their own value. Also, this is the value that is first displayed in the UI of FX Composer and 3ds Max when the material is first loaded in and the user had not made any changes to it yet. So we open this up and we see that the initial value is 0.25, 0.25, and 0.25 for the red, green, and blue, and 1.0 for the alpha transparency. And as you can see here, the color is indeed this 3 of 0.25, which results in this dark gray or charcoal like color for the sphere into which this material has been applied. Anyway, so here is an example of semantic declarations of the UI elements. We will see that with the :ambient semantic declaration, the user interface element is treated as a color picker tool. So we can click on it and we can open up the color picker and we can select any color that we want for the sphere. We selected this bright green color and we see it instantly applied. So the important thing to note is that this color is a float 4, but it considers the float 4 as a single entity, as a color, which makes selecting the color value more intuitive. However, without that semantic declaration, if we remove that, save, compile, we see that the color picker tool disappeared, and the user interface element is treated just as a regular float 4, as a collection of disjointed floating point values. So we can edit it, and here we see we are just presented with the matrix editor tool to change its value, which sets the values of all 4 floats separately. So I can, I don't know, like 0.5, and increase this to maybe 0.75. What would that look like? Did I not change it? So if I, for example, set this color all the way down to 0.1, this one is also 0.12 or something, and then I press OK. I compile it, and now the color changed. So basically, without that semantic declaration, now it treats the color as a collection of float 4 variables, which is less convenient than doing the matrix editor, because not only is the input color awkward and you don't know what color it will be in advance, but also it doesn't automatically update the color. You have to compile it in order to apply the new color onto the material. So the main point that I want to say is that the annotations, or also called as semantic declarations, are, however, not the only way to specify the UI widget that is used by the graphics app whenever we want to modify the value. These metadata members right here in the alligator jaws can also specify the UI widget, and in fact they take precedence over semantic declarations. So if a semantic declaration is specified and a metadata member is also specified to use a different UI widget for that user interface element, then that metadata member overrides the semantic declaration's settings. For example, if we return the ambient right here, this activates the color picker tool. As we see, now we have a color picker. Yeah, we have a color picker, but if I also include a metadata member, which is the string UI widget, I specify that the UI widget should be a slider instead. And when I compile it, that automatically overrides the setting that was applied when we put the semantic declaration, and the user interface element is converted into a text box, which is kind of awkward like this. It's converted into a text box. 0.3, 1.0. Sure, why not? Another example, if we remove this ambient declaration, we saw that previously the color picker tool disappeared. But if we specify the UI widget explicitly as a color, for example, this defines the color picker tool, and this defines the UI widget name. So if I save that and compile that, we see that the color picker tool comes back, because this UI widget overrides the absence of a semantic declaration statement. Yeah, so it overrides the lack of a semantic declaration. And if we set the string UI widget with the value none, you might be guessing what that does. We can see that the UI element disappears completely from the material panel, and that's because we set the UI widgets to be none, which means that there should be no any way to input it here. Okay, so these two slides are about just what I talked about. So now we will talk about the DXIL code generation of the HLSL UI elements. So this example code has a UI element which prompts the user to input a color. That color is then used as the output color of the shaded painted over the geometry, using that sum color as a float 4 and assigning it to the output color field in the vertex to pixel struct. The output struct consists of both a position vector and a color vector, and the input struct is not used. Corresponding to the declaration of the UI element in the HLSL code, a resource handle is created in the DXIL code. Its type is a struct with only an I8 pointer inside. Here, a resource represents the global variable of the UI element, which is the input from the user. And we should know that all tweakables in HLSL code, such as these user interface input elements and also the transformation matrices, as we will see later, they are all represented as handles to external resources in the DXIL code. And according to the LVM reference, resources are identified via handles passed to resource operations. Handles are represented via opaque type. Now, in the HLSL code, vertex to pixel out is declared as being initialized a zeroed out structure. We use a C-style cast to convert that 0 into a value the size of the struct all zeroed out. In the DXIL code, this is represented as moving a float 0 value into every single element in that structure. The element ID 0 is for the position, and it is 1 for the color. And we have 4 of them because both the position and the color fields in the zeroed out vertex to pixel struct, they are both float 4 data types. So notice that the column value ranges 0 through 3 for both the position 0, 1, 2, 3 and the color 0, 1, 2, 3. It is saving each of the 4 elements in the float 4 scalarized, being stored into the output from this shader. Now, from this created resource handle, which is called %1 in the LVM IR virtual registers. This is right here. A struct with 4 elements is loaded into %2. So this %dx.types.c buffered.f32 is actually a struct type definition containing 4 float values. And out of this instance of the struct %2, we load all 4 of the float values scalarized, saving them into temporary variables. Now, according to the LLVM reference, this C buffer load legacy, the operation loads 4 32-bit values from a constant buffer, which has legacy 16-byte layout. Values are then extracted via the extract value instruction, and unused values may be optimized away by the driver compiler. Then each of these variables is stored scalarized into the output. The element ID is 1 this time because only the out.color is being overwritten with the new values. The column index right here is matching the indexes of the extract value instructions above, signifying a straightforward copy of each element. So as we extracted the element at index 0 into %3, the element at index 1 into %4, and so on and so forth, here we are storing %3 into the element at index 0 of the output, %4 into the element at index 1 of the output, and so on. So that is how we are having this assignment statement right here. Now, an interesting point of noting is that in the previous version of the HLSL code, the struct object was being declared initialized to all zeros, which resulted in these store output 0.0 calls. Now, on the next slide, suppose we only change this line here. So instead of explicitly initializing all fields of the struct object to zeros, we will leave it uninitialized. Common sense from C programming tells us that the struct object will be initialized with the garbage values, but we want to see what indeed happens in this situation. So we run this modified version of the HLSL code through Shaded Playground, and we get this DXIL code as the output. Now remember that the struct holds two float-4 variables. The generated DXIL code just omits the lines of the code that zero out all 8 data elements in the struct object. The other code is unchanged. If we compare it to the previous version, here we are zeroing out the entire struct, so that creates some obligatory mandatory store outputs with 0 values, but since we're default initializing them without any particular value such as 0, we indeed see here that the compiler simply chooses to omit that code. So it is interesting that it doesn't do anything for the object declaration vertex to pixel out. Because the object remains uninitialized, no store output is performed on the elements. Then when some color is assigned into out.color, we see the store output is used with an element ID of 1 for the color field only. The position field of the struct is not initialized at all anywhere. We are only having these store outputs right here for the color field, and no store outputs are generated for the position field at all. So when the structure vertex to pixel out is returned from the vertex shader in the HLSL code, only the color field of it is actually being stored as an output in the DXIL code. Looking at the high-level HLSL code, we think that the entire structure is being returned with both of its fields. But actually, what happens is only the color field is an output from the shader. This example concludes the session Introduction to HLSL and DXIL for Beginners, Part 3. Next time, we will have the lecture on Part 4 of the presentation, which will be entirely about transformation matrices.